An animal with high visual temporal resolution can distinguish events occurring closer together in time. It receives more usable visual information from a rapidly changing scene before those changes begin to merge. This is sometimes described as experiencing time at a different speed. The phrase is useful, but not entirely precise. What scientists can measure directly is the rate at which an animal processes changing sensory information, rather than the subjective passage of time itself. One common method involves showing an animal a flashing light. At a low frequency, the light clearly switches on and off. But as the flashes become faster, they eventually merge into what appears to be a continuous glow. The point at which this happens is called the flicker fusion frequency. An animal with a higher flicker fusion frequency can continue detecting individual flashes at greater speeds. It is somewhat like comparing cameras recording at different frame rates. A camera capturing more frames every second can reveal changes that would be lost or blurred at a lower frame rate. Animal vision is considerably more complicated than a camera, but the comparison helps explain why the same movement may appear different to different species. Humans generally stop perceiving a rapidly flashing light as separate flashes somewhere around 50 or 60 times per second, although the precise threshold depends on brightness, contrast, and whether light appears within the field of vision. Some animals can detect changes far faster. The visual systems of certain flies can respond to flickering approaching 300 times per second. This ability is extremely useful for an animal that flies rapidly through a complicated environment while avoiding obstacles, predators, and attempts to swat it. A human hand moving towards a fly may therefore provide the insect with more successive visual updates than the human performing the movement receives. This does not necessarily mean the fly consciously watches the world in cinematic slow motion, but it does mean its nervous system can extract useful information from much faster changes. Birds can also possess extremely high temporal resolution. This makes sense for animals traveling quickly through forests, pursuing insects or changing direction while surrounded by branches and other birds. In experiments, collared flycatchers detected flickering at rates exceeding 140 times per second under bright conditions. At a frequency that already appears continuous to a human, the bird may still detect repeated flashes. This difference can even affect how animals experience human technology. Dogs have been shown to detect faster flickering than humans. An older television with a relatively low refresh rate could therefore appear reasonably smooth to a person while looking less continuous to a dog. Modern screens refresh more rapidly, making the separation between individual images less noticeable. But high temporal resolution is not automatically better in every situation. Processing rapid changes requires energy, and vision must make compromises. To see clearly in darkness, an eye needs to collect enough light. One way to do this is to combine incoming light over a longer period, rather like leaving a camera shutter open. This improves sensitivity, but it also reduces the ability to distinguish events occurring close together. Fast movements may become blurred, but faint objects become easier to detect. An animal active in bright daylight can afford to process shorter samples because plenty of light is available. A nocturnal animal may benefit more from gathering limited light than from detecting every rapid change. The box jellyfish provides an extreme example. Although it possesses surprisingly complex eyes, studies of some of those eyes found flicker fusion frequencies of only around 8 to 10 times per second. Its visual system is not attempting to resolve the world in the same way as that of a fast-flying bird. Instead, its eyes are adapted to the information needed for its own behavior and environment. Across many vertebrate species, researchers have found a general connection between temporal resolution, body size, and metabolism. Smaller animals with fast metabolisms often process visual changes more rapidly than larger animals. A small animal operates on a different physical scale. Its heart may beat faster, its movements may be quicker, and nearby objects can cross its field of vision extremely rapidly. A delay that would be insignificant to an elephant could represent a substantial part of a fly's escape time. Greater temporal resolution can therefore provide smaller, faster animals with enough information to react before an event is already over. But body size alone does not determine visual speed. Lifestyle is also important. An animal that pursues fast prey, flies between obstacles, or must evade sudden attacks, benefits from detecting rapid changes. An animal that moves slowly, lives in darkness, or depends more heavily on smell may face very different evolutionary pressures. Even members of the same broad group can therefore possess different visual abilities. Light levels also change performance within a single animal. A visual system that distinguishes extremely rapid flickering in bright daylight may become slower as conditions grow darker. This is because the eye must spend longer collecting light before forming a reliable signal. The rate at which an animal perceives visual change is not fixed like the frame rate of a video. It shifts with brightness, contrast, movement, and the part of the eye receiving the image. And vision is only one component of time perception. Animals also use hearing, touch, memory, attention, and internal biological clocks. A hummingbird timing its arrival at a flower, a predator anticipating the movement of prey, and a migrating animal responding to the changing seasons are all dealing with time at very different scales. Flickr experiments do not reveal the complete subjective experience of any of them. They do, however, demonstrate that 1 second does not provide every animal with the same visual information. For a relatively slow visual system, rapid events can merge together. For a faster one, the same interval can contain a greater number of detectable changes. The fly escaping a hand is not outside time. It simply possesses a visual system adapted to find information within moments that pass too quickly for us to see.